Assalamu alaikum, Bismillah Rahman Rahim. I will be reading Physics for Scientists and Engineer by Survey and Jewett, Section 1.2, Modeling and Alternative Representations. Most courses in general physics require the students to learn the skills of problem solving, and examinations usually include problems that test such skills. This section describes some useful ideas that will enable you to enhance your understanding of physical concepts, increase your accuracy in solving problems, eliminate initial panic or lack of direction in approaching a problem, and organize your work. One of the primary problem solving methods in physics is to form an appropriate model of the problem. A model is a simplified substitute for the real problem that allows us to solve the problem in a relatively simple way. As long as the prediction of the model agree to our satisfaction with the actual behavior of the real system, the model is valid. If the prediction do not agree, the model must be refined or replaced with another model. The power of modeling is in its ability to reduce a wide variety of very complex problems to a limited number of classes of problems that can be approached in similar ways. In science, a model is very different from, for example, an architect scale model of a proposed building which appears as a smaller version of what it represents. A scientific model is a theoretical construct and may have no visual similarity to the physical problem. A simple application of modeling is presented in example 1.1, and we shall encounter many more examples of the models as the text progresses. Models are needed because the actual operation of the universe is extremely complicated. Suppose, for example, we are asked to solve a problem about Earth's motion around the Sun. The Earth is very complicated with many processes occurring simultaneously. These processes include weather, seismic activity, and ocean movements, as well as the multitude of processes involving human activity. Trying to maintain knowledge and understanding of all these processes is an impossible task. The modeling approach recognizes that none of these processes affect the motion of the Earth around the Sun to a measurable degree. Therefore, these details are all ignored. In addition, as we shall find in chapter 13, the size of the Earth does not affect the gravitational force between the Earth and the Sun. Only the masses of the Earth and the Sun and the distance between their center determine this force. In a simplified model, the Earth is imagined to be a particle, an object with mass but zero size. The replacement of an extended object by a particle is called the particle model, which is used extensively in physics. By analyzing the motion of the particle with the mass of the Earth in orbit around the Sun, we find that the prediction of the particle's model are in excellent agreement with the actual motion of the Earth. The two primary conditions for using the particle model are as follows. Number one, the size of the actual object is of no consequence in the analysis of its motion. Number two, any internal processes occurring in the object are of no consequence in the analysis of its motion. Both of these conditions are in action in modeling the Earth as a particle. Its radius is not a factor in determining its motion, and the internal processes such as thunderstorms, earthquakes, and manufacturing processes can be ignored. Four categories of the models used in this book will help us understand and solve physics problems. The first category is the geometric model. In this model, we form a geometric construction that represents the real situation. We then set aside the real problem and perform an analysis of the geometric construction. Consider a popular problem in elementary trigonometry as in the following example. Example 1.1. Finding the height of a tree. You wish to find the height of a tree but cannot measure it directly. You stand 50 meters from the tree and determine that a line of sight from the ground to the top of the tree makes an angle of 25 degrees with the ground. How tall is the tree? Figure 1.2 shows the tree and a right triangle corresponding to the information in the problem superimposed over it. We assume that the tree is exactly perpendicular to a perfectly flat ground. In the triangle, we know the length of the horizontal leg and the angle between the hypotenuse and the horizontal leg. We can find the height of the tree by calculating the length of the vertical leg. We do so with the tangent function. Figure 1.2, example 1.1. The height of the tree can be found by measuring the distance from the tree and the angle of sight to the top above the ground. This problem is a simple example of geometrically modeling the actual problem. Tan theta is equal to opposite side over adjacent side. The opposite side is h, the adjacent side is 50 meter, theta is equal to 25 degrees. From this we can calculate the height, which comes out to be 23.3 meters. You may have solved a problem very similar to example 1.1, but never thought about the notion of modeling. From the modeling approach, however, once we draw the triangle in figure 1.2, the triangle is a geometric model of the real problem. It is a substitute. Until we reach the end of the problem, we do not imagine the problem to be about a tree, but to be about a triangle. We use trigonometry to find the vertical leg of the triangle, leading to a value of 23.3 meter. Because this leg represents the height of the tree, we can now return to the original problem and claim that the height of the tree is 23.3 meter. Other examples of geometric models include modeling the earth as a perfect sphere, a prism as a perfect disk, a meter stick as a long rod with no thickness, and an electric wire as a long straight cylinder. The particle model is an example of the second category of models, which we call simplification models. In a simplification model, details that are not significant in determining the outcome of the problem are ignored. When we study rotation in chapter 10, objects will be modeled as rigid objects. All the molecules in a rigid object maintain their exact position with respect to one another. We adopt the simplification model because a spinning rock is much easier to analyze than a spinning block of gelatin, which is not a rigid object. Other simplification models will assume that quantities such as the friction forces are negligible, remain constant, or are proportional to some power of the object's speed. We will assume uniform metal beam in chapter 12, laminar flow of fluids in chapter 14, massless spring in chapter 15, symmetric distribution of electric charge in chapter 23, resistance-free wires in chapter 27, thin lenses in chapter 34. These and many more are simplification models. The third category is that of analysis model, which are general type of problems that we have solved before. An important technique in problem solving is to cast a new problem into a form similar to the one we have already solved and which can be used as a model. As we shall see, there are about 24 analysis models that can be used to solve most of the problems you will encounter. All the analysis model in classical physics will be based on four simplification models: particle, system, rigid object, and wave. We will see our first analysis model in chapter 2, where we will discuss them in more detail. The fourth category of models is structural models. These models are generally used to understand the behavior of the system that is far different in scale from a macroscopic world. either much smaller or much larger, so that we cannot interact with it directly. As an example, the notion of hydrogen atom as an electron in circular orbit around a proton is the structural model of the atom. The ancient geocentric model of the universe, in which Earth is theorized to be at the center of the universe, is an example of a structural model for something larger in scale than our macroscopic world. Intimately related to the notion of the modeling is that of forming alternative representation of the problem that you're solving. A representation is a method of viewing or presenting information related to the problem. Scientists must be able to communicate complex ideas to individuals without scientific backgrounds. The best representation to use in conveying the information successfully will vary from one individual to the next. Some will be convinced by a well drawn graph, and others will require a picture. Physicists are often persuaded to agree with a point of view by examining an equation, but non physicists may not be convinced by this mathematical representation of the information. A word problem, such as those at the end of the chapters in this book, is one representation of a problem. In the real world that you will enter after graduation, the initial representation of the problem may be just an existing situation, such as the effect of climate change or a patient in danger of dying. You may have to identify the important data and information and then cast the situation yourself into an equivalent word problem. Considering alternative representations can help you think about the information in the problem in several different ways to help you understand and solve it. Several types of representations can be of assistance in this endeavor. Mental representation. From the description of the problem, imagine a scene that describes what is happening in the word problem. Then let time progress so that you can understand the situation and can predict what changes will occur in the situation. This step is crucial in approaching every problem. Pictorial representation. Drawing a picture of the situation described in the word problem can be of great assistance in understanding the problem. In example 1.1, the pictorial representation in figure 1.2 allows us to identify the triangle as a geometric model of the problem. In architecture, a blueprint is a pictorial representation of a proposed building. Generally, a pictorial representation describes what you would see if you were observing the situation in the problem. For example, figure 1.3 shows a pictorial representation of a baseball player hitting a short pop foul. Any coordinate axis included in your pictorial representation will be in two dimensions, x and y axis. Simplified pictorial representation. It is often useful to redraw the pictorial representation without complicating details by applying a simplification model. This process is similar to the discussion of the particle model described earlier. In a pictorial representation of the Earth in orbit around the Sun, you might draw the Earth and the Sun as spheres, with possibly some attempt to draw continents to identify which sphere is the Earth. In the simplified pictorial representation, the Earth and the Sun would be drawn simply as dots, representing particles with appropriate labels. Figure 1.4 shows a simplified pictorial representation corresponding to the pictorial representation of the baseball trajectory in figure 1.3. The notations Vx and Vy refer to the component of the velocity vector for the baseball. We shall study vector components in chapter 3. We shall use such simplified pictorial representation throughout the book. Graphical representation. In some problems, drawing a graph that describes the situation can be very helpful. In mechanics, for example, position time graphs can be of great assistance. Similarly, in thermodynamics, pressure volume graphs are essential to understanding. Figure 1.5 shows a graphical representation of the position as a function of time of a block on the end of a vertical spring as it oscillates up and down. Such a graph is helpful for understanding simple harmonic motion, which we study in chapter 15. A graphical representation is different from a pictorial representation, which is also a two-dimensional display of information, but whose axes, if any, represent length coordinates. In a graphical representation, the axis may represent any two related variables. For example, a graphical representation may have axes for temperature and time. The graph in figure 1.5 has axes of vertical position y and time t. Therefore, in comparison to a pictorial representation, a graphical representation is generally not something you would see when observing the situation in the problem with your eyes. Tabular representation. It is sometimes helpful to organize the information in tabular form to make it clearer. For example, some students find that making tables of known quantities and unknown quantities is helpful. The periodic table of the element is an extremely useful tabular representation of information in chemistry and physics. Mathematical representation. The ultimate goal in solving a problem is often the mathematical representation. You want to move from the information contained in the word problem through various representation of the problem that allows you to understand what is happening to one or more equations that represent the situation in the problem and that can be solved mathematically for the desired result. Thank you for your time. Allah Hafiz.